notes for 11.9. You can kind of see that it's split up classwork and homework. But really, we're going to do not all, but a chunk of the homework part in class today. And then, like I said, you may have 3 or 4 of those graphs to finish for homework today. So we'll see. Maybe we'll get through more of it than we did last period. Most of this is review. So I think I'm going to try to go a little faster than I went last period. If I go too fast, then by all means stop, because we had barely enough time. So there is time. If something is not making sense, definitely raise your hand or holler out or something, and we'll slow it down. But most of this you've seen before, and so it's kind of just presenting it in a different way, and we land at a spot that we haven't quite done before. All right, we now turn to analyzing functions via calculus. We did this in pre-cal by determining the zeros of the function, where it crosses the x-axis, and the sign of the function between the zeros. I don't even know that we did that second part, but you definitely found zeros in pre-cal, which gives us some information about the function, but little clue as to its actual shape. Calculus will provide the missing pieces to the puzzle. So we know this. First derivative tells us increasing, decreasing. Second derivative tells us concavity. That's what this whole page is about. So you kind of know this already. I think you do know this already. Let's just kind of breeze through this and get to that second page. A function is increasing if the y value goes up. Okay. Although you do have to remember that you're moving to the right. Like you read a graph, like you read a book. So it's especially tricky when there's an asymptote somewhere. Because if something like that, is that graph increasing or decreasing? It's decreasing. So it's like, well, it's going up right there. I mean, yeah, but that's reading it backwards. As you read it from left to right, that graph is decreasing. So make sure you're reading your graphs from left to right. So yeah, you know that's decreasing, that's constant, that's increasing. Increasing curves come in 3 varieties. In each case, let's draw tangent lines at 3 points along the curve. So I inserted that little extra there to make sure we're kind of all on the same page. So pick a point at each end and then in the middle, and draw a tangent line. It's almost tricky easy on the first one. It's like, how am I supposed to draw a tangent line that is the line? So yeah, that's a little bit odd. Makes a little more sense on the next 2. So pick 3 points. Do a little tangent line pieces. You don't have to do the full line because then they overlap and then it looks a little bit crazy. So tangent line segments almost is a better way to say it. Okay, the question then is, what is true about the slope of the tangent lines at all of those points? So we did 9 points. What's true about all 9 slopes? Be careful. I wouldn't say the slopes are increasing, but they are positive. So f prime is positive. Not f prime is increasing, because like on this last one, f prime is not increasing. F prime is actually decreasing, even though the slopes are positive. And we know this. If f prime is positive, that means f is increasing. That's kind of how we started this. These are all increasing curves, and so all of their slopes, anywhere you put them, their slopes are positive. Decreasing curves come in 3 varieties, as shown. So it's real similar to the last thing we just did. Let's draw tangent lines at 3 points along the curve. So same thing. Pick a point at each end, a point in the middle, and draw the tangent line. Or the tangent line segment, I guess, if you don't want to draw the whole line. what is true about the slope of all of those tangent lines? That they're negative. F prime is negative because f is decreasing. Or you can say it the other way, f is decreasing because f prime is negative. So those always go together. Those say the same thing. But before you turn the page, like you can guess where this is heading, because all three of these are decreasing, but they don't look exactly the same. There's something different about all three of those. You know the word to describe it, and that's where we're headed. So we can make the following statements about increasing and decreasing functions. Let f be a function that is continuous and differentiable. Again, it's always continuous on the closed, regardless of what we're talking about, and differentiable on the open. So that's rarely tested that finely on the AP test, but MVT or rolls or just about anything, continuous on the closed, differentiable on the open. If f prime is greater than 0, then f is increasing. Okay, yeah, we know that. If f prime is less than 0, that means the slope is negative, then f is decreasing. We know that. If f prime is 0, then f is constant. So yeah, increasing, decreasing, constant. We're good with that. That was kind of partially what was tested on the last test. When we examine functions that have curves to them, we will define their curvature in terms of concavity. Concavity comes in two flavors, concave up and concave down. We call this curve concave up, and you know this, but this is good review. The term that this guy likes to use is holds water. If water is poured into this structure, it will collect and hold. The one problem with holds water, and the author of this worksheet knows that, that's why he puts it in parentheses, is that, let's say you had something that looked like that. Is that concave up or concave down? Concave up. Will it hold water? No. So that's why he puts it in quotes, because he knows that if you have a full turn, then sure, it would hold water, but you could be concave up and not hold water. So you got to be careful with that phrasing. I mean, I see what he means, and I've used the term bold up and bold down, but be careful with holds water. On the concave up curve, draw tangent lines, again, like line segments would be a better way to say it, otherwise you're going to have lines everywhere, at the points shown. So just little line segment pieces, little slope pieces there. As we move from left to right, what's happening to the slopes? So all those little slope pieces, what's happening to the slopes as we move left to right? Which one? Because it's not... Be careful how you phrase that now. I know what you mean. They're not... On this side, they're definitely increasing. The slope is increasing. That's the easy side to see. On this side, this was like, I don't know, -10, and then -8, and -6, -2, and -1. But those are still increasing. Okay, those slopes are increasing. It feels weird to say that when the values are going down. But if you think about a number line, as you move toward the right on a number line, those numbers are increasing. So we would say that what is true about the slopes of these lines, I would say f prime is increasing. But increasing is a derivative type word. It's a rate type word. And so this means that the rate of f prime is positive. So that means we've got the derivative of a derivative. So the second derivative is positive. And that's what it means to be concave up. F prime is increasing. All right, do the same thing on the second, on the concave down curve. So I don't know, the slopes go from 10 to 8, 6 to 2 to, maybe that one's 1/2 to 0 to negative things. I don't know, just making up numbers. Yes?
Oh, you said you're making up numbers.
Yeah, you're like, how do you know that? I'm just trying to get the trend, because that's what the question is. What's happening to these slopes as we move left to right? What's happening to those slopes? Yeah, they're decreasing. Regardless of what their actual numbers are. They started out really positive, they got less and less positive, and then they went negative, and they got more and more negative. So they are decreasing. F prime is decreasing. And if f prime is decreasing, then the second derivative is negative. And that's what makes them concave down. So here's one way to define concavity, which is what we just said here. If f is differentiable, the graph of f is concave up if f prime is increasing. Maybe we should add that to our little list here just to tie it all together. If f prime is increasing, it's concave up, the second derivative is positive. If f prime is decreasing, it's concave down, and the second derivative is negative. I don't have the guy's key that wrote this, so I'm not sure what goes in these next three blanks. So I'm curious what you think. When you think slope of a tangent line, what would come to your mind? If I ask you to find the slope of a tangent line, what would you think? For slope of a tangent line?
Well, the first derivative would be the tangent line, so then taking the tangent line up to the tangent line, so that slope would be the second.
Okay. I like what you said, but I like what you said first best when you said to find a tangent line, you need a slope and a point, and that slope comes from the first derivative. F prime tells you the slope of f. Now, if you did the slope of the slope, that would be the second derivative. But tangent line to f, you're thinking the first derivative. When you think increasing, I am going to fill in this one because I still don't know exactly what he's looking for. This is what makes sense to me. If something is increasing, then its derivative is positive. If something is decreasing, then its derivative is negative. I kind of don't like this because he doesn't specify if we're talking f or f prime or f double prime. But I do like it because it holds regardless. If you think f is increasing, then f prime is positive. If you think f prime is increasing, then f double prime is positive. Because increasing or decreasing are derivative type words. So when we say f prime is increasing, then we're talking about a derivative of a derivative, which is the second derivative. So if the first derivative is increasing, that means the second derivative is positive. Concavity is related to the sign of the second derivative. Yes, we know all of that. Skip down to this little table here. I'm going to try to color code as well. If f prime is positive, that tells me that f is increasing. In fact, I'm just going to do both of those pieces. If f prime is positive, f is increasing. If f prime is negative, that tells me f is decreasing. Okay, I'm going to go with 4 colors here, so you may need to, if you want to color code yours, you're going to need to find some, you may need to borrow some from a neighbor and say, help me out here. You can have my orange if I can have your green. Let's do the same with the second derivative. If the second derivative is positive, that means we're concave up. If the second derivative is negative, then we are concave down. We're going to look at this sort of 2 by 2 square before we get to the 3 by 3 square. Because that's what's going to be, well, it's all important, but for graphing purposes, this is what's going to help us a lot. Increasing and concave up. This matches number 8 on the test that some of you were close on, but not close on. Increasing and concave up. So increasing, I know what that looks like. Concave up is something like that. So if I sort of merge those two ideas together and I want to be increasing and concave up, it should look like that. Next one over, I want to be decreasing but concave up. So I have to kind of merge these ideas of decreasing, so I'm going down, but I'm still concave up. So I want to be bold up while decreasing, so something like that. All right, this box says f is increasing, so I'm going up, but I'm concave down. So I'm bold down. So I want to be increasing but bold down. So I have to merge those ideas in my brain and be increasing but concave down. And then lastly, I want to be decreasing, but concave down. So decreasing or also concave down, not really but. Decreasing, concave down. So we'll have to kind of put all those ideas together. Tomorrow we'll get an equation and make sense of all this and put them all in a graph. Let's move over to the right-hand column here. If f prime equals 0, that would mean we have a horizontal tangent line. So let's think about this. A horizontal tangent line, but also concave up. Oh, I put my dashed line in the wrong spot if I wanted to be concave up. Horizontal tangent line, but concave up means we have a minimum. Horizontal tangent line, but concave down means we have a maximum. Earlier, you guys asked about number 4 on the test, the second derivative test. That's what this is. That's the concept of the second derivative test. If you have a horizontal tangent line, but you're also concave down, then you've got a max. You've got a horizontal tangent line, but you're concave up, and then you got a min. All right, let's come to these two, bottom two here. So f is increasing, Now, you know what, let's back up to this. If f double prime is 0, that means we have a possible inflection point. Possible inflection point. So let's do an increasing function that changes concavity. This one's a little bit harder for you to draw probably until you've seen it a couple times. It's something like that. It's increasing, but it went from concave up to concave down. So there was a point of inflection there. And then you could do the same thing on this side. Decreasing all the way, but there's a change in concavity, so there's a point of inflection. This last possibility is kind of tricky. It could look like that, where there's an inflection point there. But it can also level off and almost become flat for a little bit. That would not be a point of inflection because it's concave up the whole way. Starting tomorrow, we'll take derivatives and we'll figure out like kind of where we are on the graph so we know what shapes look like. All right, on to your homework. So time for us to get ahead of the game here. Let's talk about what these names mean, and then I'll ask you to fill in the blanks. Critical point. So what's a critical point? First derivative is 0 or undefined. In terms of a graph, how would you know the first derivative is 0 if you're looking at a graph of f? Oh, I should say that. This is a graph of f, not of f prime. So you need to be careful here. Okay, so you're doing this. It's not necessarily that, because it could be this.
So the slope is 0 on this line.
So I'm going to say a horizontal tangent line. But that's the same thing as slope is 0. So I'm looking for a place where the slope is 0. What about undefined? How would you know from a graph if a function has an undefined slope?
If it's vertical.
Vertical tangent line.
Okay. So vertical tangent line would be one. Asymptotes would be one. This graph doesn't have any asymptotes, but you're right.
Cusp.
And a cusp. I guess we should just list asymptote as well. So I'd be looking for vertical tangent lines or cusp or asymptotes. Relative minimum. How do I find a relative minimum looking at a picture? So don't use derivative, don't use calculus words, just how do I know if there's a relative minimum looking at a graph? Or show me with your hands. What are you looking for? Yeah, it's like the bottom of the valley thing. They're looking for a valley. Relative max is a mountain peak. Or I guess it could be a hill peak if it's not a sharp. If it's a rounded, it could be a hill. Stationary point, I don't know that we've used that term before, but that would be where f prime is 0. So that would be a horizontal tangent line. So that's sort of a subset of critical points. The critical points where f prime is 0 are also stationary points. Inflection point would be change in concavity. Absolute minimum and absolute maximum, hopefully those are easy. That's just the highest point and the lowest point. So unless there's a tie, there should only be one check in the absolute minimum column, and there should only be one check in the absolute maximum column. Unless it's a tie, and then you would list them both. But this one doesn't have any ties. So let's do the critical point column most of the way together. That's the hardest one, and then I'll give you a few minutes to finish it, and then we'll move on to the graphs. There's also some debate on some of these points, so you can give me your opinion if you like. How about point A? Is that a critical point? I see some no's and some yeses. Well, I'll call on the person who's got it right. So, Caitlin, why did you say yes?
Vertical tangent.
I think there's a vertical tangent line at A. Now, if you want to say, no, that's not a vertical tangent line, it's really positive, but it's not vertical. If that's true, and if that's what you're thinking, then it would not be a critical point. If you look at that and you're thinking, that looks like a vertical tangent line to me, then yes, that's a critical point because of the vertical tangent line. You don't need to put a reason on the checkbox there, but if you're kind of taking notes and want to look later, you might want to. How about B? Is B a critical point? Jacob, why is B a critical point? You're nodding yes.
Slope is 0.
Yeah, slope is 0. How about C? Is C a critical point? I saw one of these, like, I don't know. Samuel, why did you give me a shrug? Like, what's the issue with C?
Because it goes back to the same as A, sort of, but I guess if you follow the line, it's more of a curve, so I would say no. But again, it's sort of right there, so it doesn't matter.
Yeah, you're exactly right. It's like, I don't know, I can't tell. Like, it would be nice if they told me. If that's a vertical tangent line, then it's a critical point. If you're looking at that and thinking, I don't know that it gets vertical, I think it's just really negative, then it's not a critical point. So I would accept either one. That's kind of a rough question. I'm going to say yes, but if you want to object to that, you're welcome to. Because I think they're trying to make it vertical, but maybe they're not. I don't know. D is this point that's on the x-axis there. Is that a critical point? No, that slope is negative, but it just happens to be an x-intercept, so not a critical point. How about E? That's another one. You're like, well, maybe. If it is, why is it a critical point? Macy, if E is a critical point, why is it a critical point? Because slope is 0. So if you think the slope is 0 at E, then it's a critical point. If you're looking at that thinking, I don't know if it gets quite horizontal, then you would say it's not. We will give you more information. So I like this graph because it makes you think, but I don't like this graph because it's hard to tell on some of these. Maybe just a question mark. How about that? F prime equals 0? Question mark? I don't know. Can't tell. How about F? F has a clear answer. Is it a critical point? Why is it a critical point? Slope is undefined. There's no derivative at a cusp. So that's a definite yes on F. How about G? Critical point or no? We haven't seen one that looks exactly like that. They're trying to make it. They're connected. Yeah, if they weren't connected, it would also be a critical point because there wouldn't be a derivative there, so that would be something going on. But they're connected. But I think they're connected. It's not a smooth connection, so it's a cusp. You won't be able to find the derivative there. That's a good picture for the derivative on one side is positive. The derivative on the other side looks like maybe it's 0, but there's no way to figure out which one it is, so there's no derivative there. All right, I want you to take a few minutes to fill out the rest of the chart. The critical points are the hardest one. After that, I think it gets a little easier. So with a friend, with a neighbor, take just a couple minutes and figure out the rest of it, and then I'll post some answers. All right, so if you're at home, check those answers and see if you get the same thing. You may have to hit pause because we're moving on. All right, so flip it over, looking at B. We want to take the graph of f prime and somehow come up with the graph of f. Something's going on at 1. Do you recognize what's going on at 1? We've kind of done these before. Tell me something about x equals 1.
Slope goes from positive to negative.
Okay, what does that mean? That's good. Slope changes positive to negative. So what's happening at f, or on the graph of f then?
Good morning, Kingwood.
A relative
Please
max.
stand for the pledges.
Go ahead, we'll stand for the pledges.
I
We'll
pledge allegiance
honor the
to
country.
flag of the United
Got a few minutes left. So when f prime is positive, that means f is increasing. When f prime is negative, that means f is decreasing. That fits with x equals 1 being a max. We'll increase up to the max, and we'll decrease after the max. That's what makes it a max.
Decreasing on the right.
What's that?
Did you mean to put decreasing on
I sure did, thank you. And so the next thing we need to think about is concavity. So what about the slope of f prime? What about the slope of f prime? This is the graph of f prime. What would you say about that slope? It's negative. It's always negative. So that means that f double prime is negative, and that means that we're concave down the whole way. So I need to increase but be concave down, and then I need to decrease and be concave down. So increase concave down up to the point, decrease concave down after the point. Part C, f prime is always positive, so we're always increasing. Or f is always increasing. F is increasing. F is increasing. But at 0, f prime equals 0, so f has a horizontal tangent line. This side we're concave down because f prime is decreasing. This side is concave up. Now it says possible because I don't know where this is up and down. So just somewhere at 0, when x is 0, there's a horizontal tangent line. I'm increasing the whole way, but I need to be concave down and then concave up. All right, your job is to try to finish the next 3. We'll answer them tomorrow in class. So again, we took the whole class, but you only got 3 problems to try on your own.